PQ. So we can start the morning session. The first talk is by Professor PQ from Virginia, and we are happy to have him. PQ have been here for many times, and this is the first time he did it virtually. He come here virtually. He's going to talk about topological stable, finite energy, electroweak monopoles, and the prediction of sin2θW. So PQ, you can start now.
Okay. Thank you for the invitation. It is too bad that I cannot be around physically because I'm missing you guys and I'm missing also the good dinners there. Anyway, but this is the first talk that I'm giving, that I'm holding a bottle of beer here. Wow. And so, you know, usually when you drive under the influence, give a ticket, which is called DUI, driving under the influence. Now I will have a ticket, TUI, talking under the influence. Okay, so I'm. Can you hear me? Can you hear me? Hello, can you hear me?
Yeah, we can hear you.
Okay. Today I will talk about something that went in and out of fashion for some time, but there is a dedicated experiment at CERN looking for precisely the object that I'm talking about today. That is the to search for a monopole, and I will basically talk about the kind of monopole that is low in mass, meaning of the order of TeV, where presumably they can be produced at the LHC, and if by luck they could also be detected by the experiment called Nat'l at the LHC, and because there are students around, and I presume that the subject of monopole might not be so familiar to the young students. So I will quickly summarize some of the main features of monopole. Okay, and so let me define my title here. What I mean by topologically stable monopole is a monopole that is stable due to a topological conservation law, okay, which is characterized by some integer n. And for instance, a monopole with n is equal to 1 cannot change into a trivial configuration with n is equal to 0, for instance. And then next in my title, there is also the term finite energy. By that I mean the monopole is a soliton with finite mass and finite size. And the main subject is electroweak scale monopole. It means these are the monopoles whose masses are of the order of TeV, and therefore they are accessible at the LHC, and they can be searched for in an experiment like Nat'l, one of the 7 approved experiments at CERN, of which I am now a full member actually. This is in contrast to the kinds of monopoles that people have been talking about the last few decades, where those monopoles came from grand unified theories and are extremely heavy, so they cannot be produced in the lab. Okay, and so those are the monopoles that were searched for in the old days, from looking whether they come from some place in space or not. And so the question is then why do you care about monopoles? Well, there are many people that care about monopoles, okay, beginning with Dirac and then Schwinger, and then the breakthrough that Topt and Polyakov did in the mid-70s is the kind of breakthrough that I'm going to use here. Now, the question, of course, is for what reasons are we interested in monopoles? Well, it goes back a long time ago, having to do with the symmetry of Maxwell's equations and so on. And then when Dirac tried to to put that in a framework of a symmetric Maxwell equation, and in the framework of quantum theory, then he discovered something quite amazing. That is the charge quantization. And so what I will be talking here is the kind of monopole that is similar to the one that Topf and Polyakov that is monopole that comes consequences of spontaneous symmetry breaking. Okay. So quickly for the students, I would just show you. This is your E&M class. Okay. So you have the Maxwell equation, Gauss's law, Faraday's law, and the Gauss's law for the magnetic field, and Ampere's law, and so on. And so you can in electromagnetic courses, you can write all of these four Maxwell equations in a couple of equations using the four vectors, like this. Okay, F nu is the tensor containing E and B, and J nu here is the current. Okay, and F twiddle is the dual of F mu given by this. Now, what has been noticed a long time ago, that in Maxwell's equation, in the absence of in vacuum, in the absence of sources, then you have the symmetry. The F mu going to F tilde F mu, F tilde F mu goes into minus F mu, or simply speaking, E into B, B into minus E. So this is something that people knew a long time ago. But as soon as you turn on the sources, then the Maxwell's equation look very asymmetric. And so people were asking whether we can supplement the Faraday's law with a magnetic current here like this, and also the Gauss's law for the magnetic field with something that has to do with magnetic charge density or not. So if you do that, then you can find that you can have the Maxwell's equation, in the form of the tensor F mu and F mu twiddle here is quite symmetric. Okay, and this K nu here is like a magnetic current for current, and then here you can have the symmetry that I've mentioned before. Now the symmetry between current, J into K, K into minus J. So that's fine. You write that down like that. But the only problem is that now suppose you have a Coulomb-like magnetic field of a point-like magnetic monopole, just like a point charge. Okay, you write it down like this. This is like a Coulomb magnetic field. Okay, and then we know, for example, that when you write the Coulomb field for the electric charge, the surface integral here give you the flux and it gives you the charge, okay, contained within that surface. Now in this case here, that would be the magnetic charge. But the thing is that if you write B as a curve A, then this integral is 0, okay? So then there's some contradiction with this one here. So it can only be non-zero if actually this Coulomb-like magnetic field is actually composed of two terms. One that is the usual curve of A, and then the other one is something that many people have heard before, the so-called singular Dirac string. So it's like this here. So this is the Coulomb-like field here. This is the string here. Okay, this is a singular string. So and the thing is that since it's singular, so the vector field A diverges along this line here. So one can define a northern patch and a southern patch, and they are basically they can be transformed into one another at the equator by a gauge transformation here like this. This is what many people, including Dirac, have done. And so, for instance, if you can find the let's say you put your electron in the presence of the vector potential A like this, you can write down the solution for the wave function in a northern patch here, and the solution for the wave function of the southern patch is connected, can be shown to be connected by this phase transformation. Okay, and so now suppose that the wave function in northern is single value. That means when you go around phi by 2 pi, it gives you the same wave function. But then the one in the southern hemisphere here gets rotated by this, like this. So if you require that the wave function in the southern patch to be single value, okay, so this thing should be equal to 1. And that means that you get the condition that the electric charge times the magnetic charge is equal to some integer divided by 2. This is the famous Dirac quantization condition. Okay, there are lots of things that can be discussed here, but of course, we will not have much time. So, but I try to put a lot of emphasis on the Dirac quantization condition here, the requirement of the single valueness of the wave function. Right? So now, so then you might ask yourself, it's very embarrassing to have a symmetric Maxwell's equation. Now, if you take it to the quantum domain, they are stuck with a singular string. Then the question is it possible that somehow one can get rid of the string or not? And while the Dirac monopole, is plagued with the problem with the singular string. This is just pure U1 electromagnetic here, and also one has no idea how heavy it could be. Okay, now it turns out that it was realized by Topf and Polakov that if you embed that U1 into some bigger symmetry group here, then you can get rid of the Dirac string, and you can also predict the mass of the monopole. And so what they did was to write down the classical solution for the field equation that represent topologically stable finite energy. Okay, and the model that they used is a toy model, the one the so-called Georgi-Grasham SO3 model that breaks down to U1 by a triplet Higgs. Okay, so and they show that the monopole is a soliton with finite size and finite mass, and that Dirac string that was that came along with the Dirac monopole was just a gauge artifact. Okay, and now the thing is that far away from the core of the monopole, it looks exactly like the Dirac monopole. So that was very encouraging, at least within the framework of gauge theory that we started to understand in the early 70s. One might be able to find something that is not that doesn't have a singular string. So the question is, what is topologically stable? This is for the students. So I like to give more of a pedagogical definition here. So what do I mean by topologically stable here? What do I mean by finite energy? How does one find such a solution for a general class of model that contain the electromagnetic U1 as a subgroup? And most and foremost, here one doesn't just talk about these things as some abstract theoretical artifact, but something real that could be actually that could have experimental and theoretical implications. Okay, so So let me just prepare ground here for to discuss what I mean by topological stability here. So usually a gauge group is spontaneously broken down to a subgroup by a Higgs multiplet. Okay, let me call it phi A here, and you have the absolute value square of the Higgs multiplet is equal to V square. Okay, so this is A contrasted with A here. Now this stuff here looks like a sphere, quote unquote sphere in internal symmetry space. Okay, so this thing here in normally in the language of sophisticated language of people working in those fields in the early 70s and later on is called vacuum manifolds, which is the space of these vacuum expectation values of the Higgs field. Now, for instance, let's take SU2 and let's take a strip of SU2 that has three real components. So when that Higgs triplet develop a vacuum expectation value, the equation that represent that is phi1 square plus phi2 square plus phi3 square, okay, is equal to V square. And so that is in the language of people working in that field is called a two-sphere, which means it's a surface of a three-dimensional internal symmetry sphere. Okay, and just to prepare ground for later discussion, now the standard model has a complex Higgs doublet, right? So that means it has four real components. So the vacuum expectation value square of the Higgs doublet is phi1 square plus phi2 square plus phi3 square plus phi4 square is equal to V square. So, but this is the surface of a four-dimensional internal symmetry sphere, and that is called a three-sphere, S3. Now, so in this discussing solutions to the classical field equations, we are interested in how solutions of the classical field equations map the vacuum manifold like this here, okay, into the boundary of a three-dimensional space. You want to see the asymptotic value of the Higgs field at R go to infinity, okay? But the boundary of a three-dimensional space is also S2, okay? So this is to keep in mind. Now, what we are used to when we learn that in Chang and Lee or many other book is that normally the vacuum expectation value of a Higgs field is 0, 0, and then one component is non-zero, okay? And then you can get the masses of the gauge field and so on and so forth. And this vacuum expectation value here is independent of the spatial direction. This here in the language of the stuff I'm talking about is a trivial perturbative vacuum here. Okay, we are interested in the vacuum which basically whose vacuum expectation value depends on where in space you are located. That means it would depend on the direction in space. So therefore, the question that people usually ask after the paper of Toph and Polyakov is that how many times when one goes around once in the spatial on the surface of the spatial sphere, how many times does it wrap around the vacuum manifold? Okay, and so that kind of question usually is classified by the so-called second homotopy group, and you don't need to really understand much about this. Just few results is sufficient to understand what I'm going to say here. For example, for a real triplet, the vacuum manifold M here is just S2. Now it turns out that in homotopy, the second homotopy group here, pi to S2 here, is just some integer n. Okay, n goes from 0, 1, 2, 3, and so on. So, the Jordan-Grashow model with a real triplet has basically non-trivial vacuum here. The n is equal to 0, correspond to the trivial perturbative vacuum, but n is equal to 1, 2, 3, and so on is also part of the solution. So what Top and Polyakov wrote was some hedgehog ansatz, which I will show the picture in the next slide, which is a static solution here, and that corresponds to n is equal to 1. So you have a non-trivial vacuum where the Higgs field here, okay, this Higgs field here tend to the vacuum here, but it depends on the spatial direction out infinity. Now this monopole is topologically stable because it takes an infinite amount of energy to go from n equal to 1 to n equal to 0. Okay, so now far from the core, you have a magnetic field that look like a Coulomb field here with a magnetic charge G sub m here. Okay, so this is the picture of the hedgehog configuration of Top and Polyakov here. This is mapping into space S2 into S2 here. Okay, so now since we are interested in the question whether the standard model with Higgs doublet can accommodate monopole or not, then one realized on further result of homotopy that pi 2 of Sn is equal to 0 for n bigger than 2. Okay, for example, for the complex Higgs doublet of the standard model, m here is S3 and pi 2 S3 is going to 0. So there's no topologically stable monopole in the standard model as we know it. But Cho and Maison came up with another solution in that they rephrase the Higgs sector as a CP1 model. Okay, so nonlinear sigma model where the vacuum manifold is also S2. So therefore, it could be topologically stable. But it turns out that that solution that they wrote down has infinite energy. So in order to have a finite energy, they have to modify the kinetic energy term of the U1 gauge field. And that is not contained within the standard model. So some unknown physics beyond the standard model. Okay. So then the question then, of course, is, I forget about monopole coming from grand unified theories. I assume only the standard model gauge group SU3 cross SU2 cross U1. Yeah. Can one have a topological stable finite energy monopole a la Topologically within solely SU2 cross U1? The answer is yes. But one needs a real Higgs triplet of SU2. The standard model itself does not have a Higgs triplet. So then that comes to a model that I talked about a few years ago at NCTS here, and that is the model of right-handed neutrino that is non-sterile, and you could have a Majorana mass of the order of the Electroweak scale. Okay, so what do neutrinos have to do with monopole? Well, this model here has a real Higgs triplet. Okay, you say, why is that? Well, see, this is a model of non-sterile neurite with Majorana mass proportional to 246 GeV, so it's very low mass. Okay, and the gauge group is still the same gauge group as the standard model. Now, for neurite to be non-sterile, it belongs to a doublet here with some mirror charge lepton here. Okay, there are also mirror quark too, but I outside the framework of the talk, so I don't mention that. Now the Majorana mass MR here can be obtained by coupling this right-handed doublet to a complex triplet here. So when the complex triplet develop a vacuum expectation value, the Majorana mass of the oriented neutrino is proportional to Vm here. Now, since it is non-sterilized, so therefore a Z boson in principle could decay into it, right? But we know that the Z boson decay with a constraint of number of generation, light generation to be 3. So therefore the mass has to be bigger than half of the Z mass. But then that is a problem because now you have a standard model with Higgs doublet and Higgs triplet, and that violates the relationship between W and Z. At 3 level, MW is equal to mg cosine theta W is verified experimentally to a very good precision, and with modular relative correction. But if you have a Higgs triplet with a big vacuum expectation value, then this can be violated very badly. So the cure of that is you add a real triplet to it, this one here, with the same vacuum expectation value. So vacuum alignment gives you immediately at 3 level the rho is equal to 1, this relationship here. So therefore this model here automatically leads to the possibility of having a monopole a la topological. Okay. So now the thing is that there are many scalars in this model too, not just the triplet, but also doublet, and also a singlet, which is irrelevant here. Now each one of them have its own vacuum manifold. For the doublet, we know that S3. Now the complex triplet actually is S5, and so on. So the vacuum manifold of this model here is S2 times S5 times this stuff here. But then the pi 2 of that vacuum manifold is the sum of these things here. And these things are 0 here. So finally, one gets just pi 2 of S2, that's Z. So the electroweak monopole in this model is topologically stable. Okay. So we can write down the Hedgehog answer just like top and polar. And one can calculate the mass because now you have a classical static solution. So the mass is equal to energy here. Then one can calculate the mass here given by this formula. This function f here depends on the value of the self-coupling. 1 here is when lambda is equal to 0, and 1.7 is when lambda goes to infinity. So f goes between 1 and 1.8. Okay. So and the value of Vm here by phenomenology of the model is within this range here. So the mass of the monopole here is estimated to be between 900 GeV and 3 TeV. Okay, and this monopole has is a finite energy soliton with a core of radius 1 over G times Vm here, so roughly 10 to minus 16 centimeters. So it's it's small, but it's not that small. Okay, inside the virtual W and Z inside the core. Okay, so then once one gets that, one might want to say, now how does charge quantization come in this model here? Now the thing is that one can write out a topological current based on the W mu nu for the W3 field of the SU2 here, like this. So the topological current is given by this. Actually, it is conserved by topology, it's not by Nat'l theorem. Okay. So now the topological magnetic charge is defined as the volume integral of the time component of this current here. So that is what I call by the magnetic charge here, topological magnetic charge, G sub m. So after you do this integral here, then you find that G, this is SU2 weak coupling, times G sub m is equal to some integer n here. Okay. Now for n is equal to 1, just like the topological monopole, then the magnetic charge of this monopole is 1 over G. Now, since SU2 cos U1 finally break down to U1 electromagnetic here, that this G, the weak coupling here, G is actually is equal to E over sine of theta W. So therefore, the magnetic charge is actually not 1 over E, but it's sine of theta W over E. So far away from the monopole, from the core of the monopole, you have a magnetic field that look like a Coulomb-like field with a magnetic charge, which is sine of theta W over E. All right, so fine. So what does that have to do with anything? So now this is a very nice thing that John and Nick and myself we realized last summer, is that you have this monopole like this, okay, with the magnetic field. But when you have let's say an electron going around that monopole like this, in order for that electron to have a single value wave function, it has to satisfy the Dirac quantization condition, which is given by this, okay? Now, if you compare this Dirac quantization condition with the topological quantization condition, this one here, then you discover the sine actually is equal to m over 2. M is just that integer that comes from the Dirac quantization condition. Now, only m is equal to 1 is allowed because sine of theta W is less than 1. So therefore, sine squared theta W, we predict it to be 1/4, okay? M is equal to 1 here. And now this 1/4 is 0.25. You might say, well, this is not quite the right value of sine squared theta W, right? Now it turns out that value is the value of sine squared theta W at the monopole mass scale, okay? So you have to evolve it down in leading order to the Z mass. And what we did here for various monopole mass here, for various fermion families, and for various number of Higgs and triplet and so on and so forth, here we found the sine squared theta W at the Z mass to be roughly 0.231. But then the monopole mass now is constrained to be between 2 and 3 TeV. It cannot be much lighter unless you do something else. So at least at this point here, the compatibility with experiment appears to indicate that some of the, if not all, mirror fermions are very heavy. Okay, and well, the thing is that TC can tell you more about this mirror fermion. Is that we have 3 generations of standard model fermions. We also have 3 generations of mirror fermions. Now it turns out that the lightest mirror fermions are long-lived. Okay, nowadays there's a very strong interest in long-lived particles. In fact, many of these mirror fermions are long-lived particles. Okay, so what are the implications? This is the last 2 slides of my talk here. I'm amazed that I did not go over time here. Okay, so the existence in the Electroweak Neurine model of a real Higgs triplet, due to the fact that we require custodial symmetry for MW is equal to MZ cosine theta W, then gives rise to a topologically stable finite energy Electroweak monopole. And the model predicts sine squared theta W to be 1/4, which is evolved down to roughly 0.231 at the Z mass, which is actually quite surprising. Okay, now the monopole mass that at least that are constrained from the renormalization group here is between 2 and 3 TeV, are accessible at the LHC. Okay, and so therefore various experiments at the LHC, Atlas, CMS, and in particular Nat'l here can look for it. Now, if you notice that the mass of the monopole here is proportional to V sub m, the vacuum expectation value of the triplet Higgs, but the mass of the right-handed neutrino is also proportional to that. Okay, so there is a deep connection in this model between the Electroweak monopole and the non-sterile right-handed neutrino here. Okay, so the question that you might ask yourself is, okay, So this is the mass here. How do I produce that? Now you might say, okay, I can go to LHC and I collide two protons together and so on. And it turns out that in the mid 80s there were a paper by Drucker and Nosinov. Let's say that for PP collision, here because in order to produce two monopole, pair monopole for instance, even if you have the energy to do so, it's exponentially suppressed because there are very few degrees of freedom in a proton, while inside a monopole, a finite size, you have a lot of degrees of freedom. So they argue that is exponentially suppressed. Of course, this is only very heuristic. Whether it's true or not, that needs to be redone. Okay, but there's another group in England, Rajanti, Gould, and so on, that look at thermal production in heavy ion collisions. Okay, and going to so-called thermal process in which the heavy ion collide together and produce for a very short time a very strong magnetic field, and perhaps you can there's a good chance that you can produce these finite size monopoles. Okay, so you might say, fine. So what are the other LHC signals in conjunction with those of the electroweak monopole signals? Well, this is something that I've said before, but I repeat it here. The signal to look for, you see the mass of the monopole is related to the mass of right-handed neutrino. So somehow if we can look for a right-handed neutrino, then the two signals might be somehow studied together. And one might look for lepton number violating signals at high energy. For example, from the decays of neurite. Now, neurite here is a Majorana particle. It's its own antiparticle. Okay, so you can have QQ bar going to a Z that goes into neurite instead of neurite bar. Okay. Now remember that. Because the neurite is a Majorana. Now neurite can decay in, for example, if it is heavier than its charge counterpart, decay into a mirror lepton here and W, which the mirror charge lepton here decays into a regular tandem model lepton plus some singlet Higgs field here. And all of this stuff here occur at displaced vertices due to the smallness of the UCAP coupling here at this point here. Okay, this is something that TC and myself and a few students we did a look at mu into E gamma, mu to E conversion. We found that this UCAP coupling is very small, so the decay occurs at displaced vertices. So these are long-lived particles. Okay, so one can have E minus, E minus, mu minus, tau minus, tau minus, E minus, mu minus, and so on. That could occur at vertices at 1 millimeter or even tens of centimeters or more, depending on the size of GSL. So basically, the main thing of this talk here is that the model that I have written down, the electroweak neurite model, was first devised to have a seesaw mechanism that can occur at the electroweak scale, not at some very high energy scale, and that you can also detect the right-handed neutrino because they are non-sterile. But then it turns out that it contains a bonus in there, and that bonus is that the consistency with the custodial symmetry requires a real triplet, which gives you an electroweak monopole. So in fact, John and Nick and myself, we are working on some long version of this paper here, the one on sin squared theta W is going to 1/4, and the other one is going to be up here in nuclear physics B. But So we are also looking at generalizing this work to Dion solution. Okay, and there are many of you look into the revised version of my original paper here, that I also mentioned the fact that now you have a low mass, meaning 1 TeV, 2, 3 TeV mass monopole. There might be some process similar to the Rubakov-Kallen catalysis process. Okay, and this is what I'm taking a look at also. So anyway, so I basically managed to finish in 40 minutes here. Thank you and stay safe.
Thank you for this very nice summary and nice talk. So we are open to questions and comments. Yes.
Hi, thank you. This is Xiao Gang. Nice talk. I have one question under the monopole mass. So you have the monopole mass proportional to the wave of the triplets, and
Yeah.
say the mass is TeV range, and then the coupling
Yeah.
must be 10 or even bigger, right? And so you trust any calculation with such a strong coupling?
Yeah, the thing. This is one of the things that we would take a look at, because the coupling is very strong. Is that your question was, right? The monopole coupling is very strong, so that could be, for example, monopolium, for example. Okay, so that could be produced, and also the coupling with fermions is also strong, because on on two electromagnetic interaction, one side you have E and the other side you have a very strong coupling, and for that reason perturbation theory is not very good here, and for that reason the computation of the production cross section that people gave you in general cannot be trusted. It's only used as some hint of what it could be, and that is something that in fact, as far as I know, nobody has a handle on a real nice way of calculating the interaction of monopoles with other particles. Does that answer your question, Xiaogang?
Happy with the answer? He's happy. There's another question from. Can you? Okay, yeah.
Hi, thank you. Nice talk.
Thank you.
Have you considered the cosmological implications?
Not yet, but I just have some rough idea, in the sense that unlike the gut monopole with 10 to the 16 G and 17 GeV, where you really have a problem with the density, okay, and so on. That's why you need inflation. And these are TeV, and so the remnants of these monopoles here will not be much. How much it is? This is something that we will try to estimate also. But the mass of these monopoles are so much smaller. So you can imagine that by the time when the temperature reach their mass, they will annihilate like crazy, and what remains is the density of this monopole, which from my back of the envelope calculation will be much less than what we know now from our density. How much it is, I cannot say precisely. but there are certainly some interesting cosmological implication too. The question is whether this monopolium, okay, can be some form of dark matter or not. And in fact, there are a number of people like John Turnings, Sabasaki, and Sherman that look at dark monopole in one of their papers, and so that is something that I might want to look into. But I'm really interested in this Rubakov-Kallen mechanism for this monopole, whether or not biogenesis could be generated, and so on. So that this is something that I'm taking a look into. So I don't know yet the answer.
You explain this to the higher form, like dipole or monopole in the electric monopole?
Can someone repeat the question? I there's an echo, so I cannot hear very well the.
Can you hear me?
Yeah. Now I can hear you. Yeah.
Oh, okay. Can you hear me?
Yeah. Like that, I can hear you.
So I wonder if you can like do the expansion for the higher form, like dipole or quark form for this Electroweak monopole. Dipole or higher multiple expansion.
Higher multiple. Yeah, that is a very good question. We have not looked at that yet. That's although experimentally people, they just presume that they look for the low monopole n equal to 1, also n equal to 2, and so on and so forth. But how the solution, how it will look like is a very interesting thing to do. Yeah, that's a very important question. I was just basically thinking about that question this afternoon too. Thank you.
Any others?
I can see Xiang Dong here. Hi, Xiang Dong.
I think somebody is here.
Hi, BQ. Sorry, I was
Hi.
mute and haven't seen you for years.
Yeah, I haven't seen you for years, but you work with my wife, so
Yeah, you must heard a lot.
so I hear you every morning when my wife turned the computer on to listen to your lectures. Yeah.
Well, hopefully we can see each other.
Yeah. Hopefully we're not too far from each other, But anyway.
So any other questions for people?
Yes.
Yeah.
There's a question on from Q&A. Did you see the Q&A? Did you?
I'm sorry.
This one is on the Q&A.
Am I through? Can I take a sip of beer?
Okay. There's a wonderful beer.
Yeah, there's a lot of monopoles in here. I have to digest them before they escape.
So you see the question?
I'm sorry.
Did you see the question on the Q&A? Yeah, okay. So here's the question. If we stay in the electroweak Higgs doublet and not quite care about whether it is topological stable, can we find an energy finite electrostatic solution requiring only breaking sp2 plus E1 at infinity?
Yeah, well, the couple of authors that look at the standard model with only Higgs doublet, and they found out that actually it's topologically stable because they can rewrite the Higgs sector as a nonlinear sigma model, CP1, and that the second homotopy group of CP1 is like pi 2 of S2, so it's equal to Z. But the only problem is that when they start to write down the solution, then when they calculate the energy of that, then it's infinite, and so in order to prevent that, they have to modify the kinetic energy term of the U1 gauge field. And instead of minus 1/4 of b mu nu, they have to put some kind of a factor in front there, and that factor certainly comes from some unknown physics beyond the standard model, and it's fitted from experimental constraints. Okay, and so the standard model by itself with Higgs doublet, cannot, without any other new interactions, cannot have finite model.
Okay.
It might even be stable, be rephrasing in terms of a nonlinear sigma model. Okay, but it is not finite.
Okay, maybe if you can answer the question by typing in later on the Q&A section. So,
Yeah.
I'm pressure. We have to move on, and thank you.
Thank you for the invitation. Stay safe. Now it's Jiang Dong. Yeah. Now finally I listen to your lecture.
Okay, well, thank you.
Yeah.
If you allow me to share, okay, thanks a lot.
So hello.
Hi.
So next talk is by Professor Jiang Dong, and he's going to talk about the large momentum effective